But I think maybe we can wait for 2 or 3 minutes, since some people are still joining.
Mhm.
So, Yanning, shall we get it started?
Sure.
Okay, cool. So, so first of all, hi everyone. Happy New Year. Happy 2025. So, welcome to this first webinar of the DEGA webinar series in 2025. So today it's our pleasure to have Professor Yang Shen, who will be presenting to us. So first of all, let me introduce the speaker. So Yanning is an assistant professor with the ECS department at UCLA. So her research interests span the areas of machine learning, network science, and data science. She actually got her PhD from University of Minnesota in 2019. She actually received many accolades. So she was first selected as a rising star in ECS by Stanford in 2017. She received an academic grant from Microsoft for AI research, Google Research Scholar Award, Herman Fellowship in 2022, and UCI Newkirk Faculty Fellowship. And I think very recently she was selected also as one of the honoree of the MIT Review of 35 Innovators Under 35 in Asia Pacific in 2022. So today she will be sharing with us some of her most recent works working on fairness for learning over graphs. So please join me in welcoming Yanning, and the floor is yours.
Thank you very much, Tao, for the nice introduction. So, hello, everyone. Thank you very much for joining today's talk. And throughout the talk, if you have any question for clarification, please feel free to interrupt so that I can clarify on the fly. Yeah, so today, it is my great pleasure to talk about some of our recent works on fairness over graphs. Specifically, today I'm going to talk about demystifying and mitigating unfairness for learning over graphs. So there are several keywords: unfairness, learning over graphs. So I will go through them one by one. Let me see. And I believe for the audience for this seminar, graphs are not something that is unfamiliar to you. So networks are everywhere: social networks, financial, energy, flight networks, as well as brain networks, traffic networks. They can all be defined as graphs. And graphs are mathematical structures to model pairwise relations. Specifically, nodes in the graphs, there are nodes which can represent, for example, airports in flight networks, neurons in brain networks. Edges can represent flight paths between airports, roads between intersections. And there are also nodal features in most of the times, such as whether in airports, types of neurons in a brain network. So, graph machine learning algorithms or learning over graphs are trying to extract this information that is encoded in graph data, such that it can facilitate understanding on information over network graphs. And henceforth, it can gain benefits on various predictive tasks. Specifically, given a real-world network, graph machine learning algorithms trying to extract those graph structures, including edge nodes and nodal features, to help us carry out graph machine learning tasks to answer potential questions such as who are our potential friends, what items will the customer buy. And And another keyword of this talk is unfairness. So let me first start from what is unfairness in general machine learning. Recently, it has been seen that machine learning algorithms, of course, have been used very widely in various applications. However, it has been seen that machine learning algorithms also lead to potential unfair results. For example, different error rates on female-male face recognition task, different prediction accuracy based on ethnicity, and the credit approval rates are different based on genders. So, since machine learning is critical for various applications and policy making, such unfairness may lead to critical issues for these applications. There has been extensive literature on bias and unfairness in reduction in machine learning. However, in the graph domain, it's comparably underexplored. So let me first set the floor by introduce what are the fairness or unfairness that we are talking about. As someone with signal processing background, we need to define this with the equations instead of only talking on the social level. So let me introduce two group fairness notions that will be the focus of this talk. One is a statistical parity, which considers that the same positive rate is achieved for individuals in different sensitive subgroups. So those subgroups, so when I say sensitive subgroups, it means that the subgroups are differentiated based on their sensitive attributes, such as gender. Then sensitive subgroups or sensitive groups refer to, for example, female, male, or race, for example. Then sensitive groups refer to, for example, Asian, white, Black, people's ethnicity. So henceforth, the statistical parity, formally speaking, is trying to find a machine learning algorithm such that the prediction y hat of the machine learning models is equal to 1, meaning the positive prediction rate is the same regardless of which sensitive group this individual is from. And of course, we can see that this notion doesn't depend on the ground truth, y. Henceforth, another notion or definition of group fairness is equal opportunity, which says same true positive rates should be obtained between different sensitive groups. Henceforth, you can see that the key difference here is it is the probability that y hat is equal to 1 is conditioned also on y the true label is equal to 1. Okay, so it's the true positive rate. And as you can imagine, a smaller delta SP and a delta EO are more desirable. In addition, I also want to mention that these criterions give us the key intuition of the algorithm design of our work is it somehow on the high level says that the decision making should be uncorrelated to a certain level with sensitive attributes. And these group fairness notions were originally defined in machine learning domain, but they are generalizable to graph domain. So these are also the notions that we will be focusing on in this talk. Okay, so we've talked about unfairness in machine learning, but what are the potential unfairness in networks and graphs? It has been shown that there are potential bias or unfairness in networks as well. For example, users get recommended to be connected, exhibit divergence between genders. And also, works have been shown that there are unfairness in user classification and resource allocation in power grids, including one of our recent works. So that motivates us to look at unfairness in machine learning over graphs. And you may have the question that since unfairness has been learned, has been studied in general machine learning, what is so different for machine learning over graphs? As those of you who have worked on graphs and networks, you know that in addition to tabular or nodal features, there's an additional source of information, which is a graph structure. And henceforth, this additional source of useful information also becomes an additional potential source of intrinsic bias. So the challenge here is the graph structure itself has intrinsic bias. And in fact, we usually see that this associative mixing, meaning that there's a higher probability for connections between similar users according to their, for example, religion or ethnicity. Henceforth, learning over graphs that is extracting both nodal features and graph structures may amplify already existing bias. Because as we know that when we are learning over graphs, regardless of whether we are using our graph neural network or other frameworks, one of the key things that we are doing is doing information aggregation over neighbors in a GNN. And this henceforth leads to indirect use of sensitive attributes in training. So as we mentioned, fairness has been studied in graph domain, but is comparably underexplored, especially that there's most of the existing works focus on specific design or, for example, adversarial regularization for the model. Henceforth, they usually lack theoretical understanding and are mostly designed for specific learning tasks. Henceforth, this motivates our work in dive into theoretically understand what is the reason or source of unfairness in learning over graphs so that we can design general frameworks for example, representation learning as well as generative models for learning over graphs based on these theoretical findings. So let's first look at a real-world example of whether that unfairness or those potential structural bias really exist in real-world networks. So this is statistics of a real-world social network. And specifically, I would like to invite you to focus on this intra and inter-edge counts. So you can see that for these real-world social networks, we see that considerably higher intra-group edges, which means that edges that are connecting nodes from same sensitive group, while inter-group edges are edges that are connecting nodes from different sensitive groups. So we can see that it indeed exhibit severely unbiased edges. And this validates our original assumption, says that there's a higher probability for connection based on between similar users. And henceforth, we want making use of such a graph structure may lead to potential bias. But in order to understand how this structural imbalance will lead to unfairness in learning over graphs, we need to understand, we need to dive into into the learning mechanism of learning over graphs. So let's look at a simple graph neural network structure. And we want to answer the question that can we actually explain the source of bias? And based on how graph neural networks learn and aggregate information. So this is a general framework of graph neural networks, how the representation in the else layer were obtained from previous layers. And as a signal processing background, I like to define everything, but you don't need to pay attention to those. Henceforth, what I only need to focus on is this equation where in this red box, where I already rewrite this layer-wise propagation or layer-wise operation into a layer-wise and a node-wise representation. What it says is the hidden representation at the else layer of the ith node is obtained by some nonlinear operation and this neural network weights. Inside, this is trying to taking average, as I mentioned, this is a basic graph neural network, is trying to take average of the hidden representation of the nodes of the neighbors hidden representation from the previous layer. Okay, henceforth, this averaging or obtaining or aggregating information from neighbors says that this is how graph structure is being used. So let's look at the two examples that it look like this, and we've color-coded the nodes based on their sensitive attributes. Now it's a binary sensitive attributes. So let's see what this learning mechanism will lead to. Let's consider that we are trying to obtain the hidden representation of node A, which is the blue node. Okay, and if the graph has this type of structure that nodes in the same sensitive groups tends to be connected with each other, where this based on this aggregation, the representation of A will be obtained by aggregating the hidden representation from its neighbors, which is a B, C, D. And then in the second layer, each of the nodes will obtain their hidden representation from by aggregating the information from their neighbors. So if this graph has this structural property that blue nodes tend to be connected with blue nodes, then that means as I am aggregating layer by layer, node A as a blue node, its hidden representation will be dominantly obtained or from blue nodes hidden representation. So if the nodal features originally has bias, this aggregation over neighbors with same sensitive groups will actually increase this correlation. And as I mentioned previously when we talk about group fairness notion, so we say that the intuition here is that the decision making should not depend on or should be uncorrelated with the sensitive attributes. So this type of aggregation will actually increase the correlation and henceforth increase the intrinsic bias. Okay, so based on this observation, now we can do some analysis based on this observation. So we use the correlation between the aggregated information in each layer and the sensitive attributes as a measure to measure the bias. Okay, and henceforth, our goal is to find this bound of this rho, which is a correlation between the hidden representation and the sensitive attributes. So through theoretical analysis, we find that this rho is relevant to different properties of the network. Specifically, let's focus on three different terms: delta, gamma 1, and gamma 2. Okay, so there are a lot of notations, but on the high level, what it says is delta says that the mean of the discrepancy between the mean of different sensitive groups of the features matters. Henceforth, the distribution of hidden representation or distribution of features matters. We want the discrepancy of the distribution, the smaller, the better. Secondly, gamma 1, which says there are a lot of notations again. Whenever you see a chi, it means cross group. Whenever you see a omega, it means within group. So on the high level, gamma 1 says that node population matters. Whether a node is connect with only within the group or also across group matters. Gamma 2 says that number of inter and intra-edge ratio matters. Okay, so specifically, you can see that dm chi and dm omega denotes the inter and intra edges of node M. And you can see if all the nodes have the same number of inter and intra edges, then this term will be 1/2, and this gamma 2 will be equal to 0. Okay, but on the high level, as I said, if we ignore all these mathematical definitions, the take-home message is a feature distribution matters, node population matters, and the age ratio matters. So based on this analysis, it motivates us to design augmentation design, because we can then design feature masking algorithms to reduce this term to make the distribution of the features from the two sensitive groups similar. Because node population matters, based on this criterion, we can design which node to sample. Because in age ratio matters, based on this term, we can design age augmentation schemes to efficiently reduce all these three terms so that the upper bound of the bias measure is reduced. Henceforth, ideally, the bias will be reduced. Okay, so let's see some performance of this algorithm. So again, we use a fairness metric as delta SP and delta EO, and let me remind you that they should be the smaller, the better. We run experiments on real social networks. And to make it easier, the x-axis is the accuracy, y-axis is the bias measures. So as we mentioned, the bias measures should be smaller the better. Accuracy should be the higher the better. So henceforth, lower right corners should be better. And henceforth, we observe that our framework always outperforms state-of-art baselines in a sense that it always obtains better fairness and accuracy or utility trade-off. Okay, so this algorithm is one of our first try of reducing bias in learning over graphs. And you can see that we design an efficient data augmentation scheme based on theoretical analysis. However, till here, we asked our question is that if we preprocess or augment the data from the very beginning, then any data that has been thrown away or is not sampled will just be lost, everything. Henceforth, useful information that has been thrown away cannot be retrieved in training. So that motivates us to think further to say, can we develop in-processing schemes so that we develop end-to-end training such that we do not directly sample or augment the input data. Instead, we develop in-processing schemes so that useful information will be pretend. This leads to our fair normalization algorithm. Specifically, this algorithm is based on the analysis, and we have already seen part of the analysis before, is, as we mentioned, the distribution of the representations matters. Ideally, we want the distribution of the features to be as similar as possible so that the machine learning algorithm cannot discriminate them. I'll give you a toy example. For example, if the embedding of two sensitive groups look like this, then they have then the machine these two distributions are considerably different. Henceforth, it may lead to potential bias for decision making. However, if the feature hidden representation of the two sensitive groups are distributed look like this, then the algorithms cannot discriminate these two groups based on their sensitive attributes. Okay, so henceforth, and this is of course also supported out by our theoretical analysis that the distribution the discrepancy in distribution is a source of bias. So the idea is, can we shift group-wise distribution in each layer to reduce such unfairness? Okay, so this motivates us to develop a fairness-aware group-wise trainable batch normalization. So you may already be familiar with batch normalization, which is a trainable layer that is usually used in machine learning in neural networks to make the training more stable and improve the training convergence speed. Okay, but it has not been used for fairness before. But so henceforth, what we developed is we say that we instead of using a batch normalization over the entire data set, what we developed is we apply a batch normalization in a group-wise way, meaning that the batch normalization layer is trained for each and every sensitive group separately. So this superscript n is is the group index. Okay, and this scheme and here gamma, alpha, beta, they are all trainable parameters. Okay, so it's slightly different from the normalization that we think about because they are all trainable parameters in these layers. So henceforth, if we can train these group-wise normalization layers, then since the mean and the variance of layer-wise hidden representation can all be represented by these trainable variables gamma, alpha, and beta. Henceforth, we can introduce regularization terms to bring these distributions in each layer close by adding this as a regularization in training. Okay, so then after this end-to-end training, the obtained distribution of the hidden representation from each and every group will be similar to each other. Okay, so in addition, we also show that this type of group-wise normalization can act as a preconditioner and provide provably faster convergence for GNN training. Okay. So here we also provided the numerical results. So through this fair norm, what we can see is that, again, the lower right corner is better with higher accuracy and a lower statistical parity, means better results. You can see that the fair norm indeed achieves very good trade-off between fairness and utility. In addition, as I mentioned, that we show that provably the algorithm provide faster convergence. We also experimentally validate whether this is the case. We can see that the red line is the GN training convergence speed with when no normalization is applied, and this is our fair norm. You can see that it always achieves faster convergence than no normalization when no normalization is used, and it achieves a similar convergence speed as if we only use one normalization layer without the group-wise normalization. So it indeed provides faster convergence than no normalization is being used. Okay, so and this is our fair norm work. Due to the limit of time, I will not be able to go through this part, which is a fairness-aware graph filter design. But I just want to mention it because as someone with signal processing background, that I cannot let myself not think about graph filtering because different from a machine general computer science point of view, as signal processing background, we say, what is bias? Bias is just something that is unwanted. So if we have a signal and there's something that we don't want it, what we do, we filter it out. So that motivates us to design fairness-aware graph filters. And this is a joint work with Professor Gonzalo Matias from University of Rochester. And henceforth we design what we did is we analyze what are in the graph frequency domain, what are the frequencies that may lead to higher bias, leads to more bias. And then we filter out this graph frequency that are correlated with bias. So the reason that I included here is because then we can apply this graph filter in each and every GNN layers directly. And this is somehow act like a batch normalization layer that is very similar to the algorithm that I already talked about. The difference is instead of end-to-end training of a batch normalization layer, we actually used first of all, the frequency domain analysis to analyze and design the filter. Henceforth, the filter is pre-trained and can be inserted. It can only need to be learned once. Okay, so. But as I mentioned that I will not be able to go through the details of this work, and for those who are interested, you can check our work. So at this point, the reason is because I want to move on further and ask an additional question. Because before I said, okay, pre-processing is not ideal because we throw away useful information that cannot be retrieved during training. Henceforth, we develop end-to-end training mechanism which use in-processing and layer-wise or group-wise batch normalization. However, this all build upon the fact that we have access to the training data and the real training data so that we can manipulate them. But what if we do not want to share real training data, for example, due to privacy concerns? And just to mention that privacy concerns is even more critical whenever we talk about fairness, because there's sensitive attributes that we may not even be able to get access to, right? So this motivates us to move further to look at the graph generative models. And graph generative models has recently been attracting a lot of more and more attention because generative models in general are more and more popular. So henceforth, to look at the fairness-aware graph generative models, my student and I need to first answer the question that whether bias of unfairness is indeed a problem in graph generative model. So to begin with, we looked at one of the SOTA algorithms in graph generative models called graph maker. And what we did is we trained a graph neural network based on G, which is the ground truth, which is the original real graph, and the synthetic graph that is obtained from graph maker based on G. Okay, so we know that for what is a good property of synthetic graph is hopefully we can get good accuracy, right? Even if we trained a model based on the synthetic graph, which from this column we can see that the accuracy, indeed, the graph maker is quite capable of preserving the accuracy. Okay. However, at the same time, let's look at the fairness measure. We can see that while or when a model is trained on original graphs, there's the bias. Such bias is amplified when we train the model based on synthetic graph. Okay, so we can see that using generated graph increases unfairness. This intuitively makes sense because we know that the generative model is trying to capture the prevailing structure in the graph. Henceforth, if a bias is indeed an issue, it also tends to amplify such bias by repetitively generating such type of bias the structure. Okay, so faced with this challenge, this really motivates us to say that, okay, for generative model, it really not only inherit the bias, but increase or introduce additional bias. So henceforth, we try to explain, try to analyze what are the source of bias in a stochastic graph model. It's different from previous analysis. So here, I cannot go into details into analysis, but I want to emphasize what is more challenging in this work is different from previous work, which is based on a deterministic graph view or the input data for a graph generative model, since it is based on stochastic models. So it leads us, make it necessary to analyze the source of bias in a stochastic graph model. So our analysis shows that the bias or statistical parity is relevant to these two terms, alpha 1 and alpha 2. Okay. Here you can see that SK is the number of nodes, the population in each sensitive groups. And this P kappa chi is the expected value of number of interedges and the expected number of intraedges. So henceforth, you can see that the bias is relevant to these two terms. And this motivates us to, the intuition is we again want to achieve a certain type of balance between inter and intra-edges is more desirable. But that by balance does not mean that they should be exactly equal. It just means that they should be designed to reduce these two alpha 1 and alpha 2s. So this analysis guide us to introduce a regularizer during training. And there are a lot of notations again, but the high level idea is this regularization is introduced to reduce this delta SP. Okay, and it is designed in a way such that it allows mini batch application during training without the need of accessing the entire graph data. And this can be applicable to any model that output probabilities for edges in graphs. For example, GN training for link prediction, as well as graph generative models that I will talk more about. So based on this analysis and the design the regularizer, we developed a FairWire, which is a diffusion model for graph generation. And not only the graph can be generated, it also generates the corresponding sensitive attributes. So the idea is that the FairWire will generate graphs with similar distribution of to the original graph G, but at the same time, it will reduce the structural bias. Okay, and the fact that it also generates sensitive attributes allows fair model training without sharing sensitive information. So I want to give you a big picture. Some of you may already be familiar with what is a graph generative model or diffusion model for graph generation. It consists given a ground truth graph, it consists noise addition step, where in each step it is adding discrete noise in terms of edge deletion and edge addition. And it also consists another part that is denoising model that is parameterized by theta, and this theta is going to be trained. So the idea is that after the denoising, the obtained graph G tilde is similar to the original graph G. Okay, and henceforth, the training depends on the training loss usually consists the cross entropy to measure the difference between G and G tilde. At the same time, in addition, in order to promote fairness, we add our proposed regularization. So let's look at some results. When we tested our results on 6 real-world net data, and we tested the performance on both node classification and the link prediction tasks. So I want to clarify what is the training mechanisms. Specifically, what we did is we generate a synthetic graph to train these node classification and the link prediction tasks, while the real graphs are only used for evaluation of these models. Okay, so let's look at some of the performance. And here, G is the case where the model is trained on the original or the real world graph. And the G tilde corresponds to graph maker, which is the fairness ignorant graph generative model. And FairWire is our proposed method. So you can see that compared with the fairness agnostic graph generative model, the proposed method achieves similar utility. At the same time, the corresponding fairness measures, delta SP and delta SEO, is significantly lower than the graph maker. In addition, it is also significantly lower than if we use the original graph as the training data. Okay, so henceforth, it achieves a better fairness utility trade-off compared with other fairness aware and the fairness agnostic baselines. Okay, let me conclude. So in this talk, I went through several works, and Specifically, we discussed the theoretical analysis for the source of bias in different GNN frameworks. And we designed fairness-aware models such as augmentation and normalization that can be applicable in different stages of learning, including pre-processing and in-processing. We also discussed fair graph generation, which is a diffusion-based fairness-aware graph generative framework, and it enables private fair model training without sharing sensitive information. In addition, from the performance, we see that the algorithm also not only preserves the utility, but also significantly reduce the bias in the results. And we showed experimental results on real-world data sets, which validates improvements in fairness measures with similar utility. And here are the related papers that are covered in this talk. Some are not covered. We also have another line of work working on online decision-making on long-term fairness, because in this talk, I covered everything is static, that the data is available at batch. And as you can see, that most of the work, even though I'm here presenting, most of the work are done by my students, especially my fifth-year student, Dennis Coles, and she is also currently on the job market if anyone has a position. And with that, I want to also thank all the funding agencies that support the research of my group, and open for questions. Thank you for your attention.
Yeah, so thanks Yanning for the very nice talk. So actually I've been during the talk several questions already lined up. I don't know if you can see them, or do you want me to read it out for you?
Yeah, that would be great because I don't see questions on my screen.
Okay, cool. Or maybe I can also ask, well, maybe if the poster is around, maybe he or she can ask like by unmuting. So may I know if Pi Boston is here? Okay, anyway, maybe I can just try to repeat his question. So he said that, well, humans are innately biased, so perhaps unfairness must be clearly defined. So, however, societal norms drive perceived fairness. So there are perhaps far too many factors. And so what is the ground truth here, in your opinion?
So you mean what is the ground truth of what is fair, right?
I guess so.
I see. That's a very good question. And I think, however, that's a good question that I don't have an answer to, because I don't think that there's a ground truth of fairness. That is also why there are many different notions of fairness. Even in our experiments, we use the statistical parity and equal opportunity, which are two widely used group fairness notions. There are also other fairness notions, such as individual fairness and accuracy parity. So there's really not, I would say, not a one-fits-all solution. I believe that in general, which notion that people use depend on the application and the goal of the designer. What I see usually is, for example, for college admission, maybe they are interested in more the positive rate. But for example, in actual classification, then maybe the true positive rate or even the accuracy parity is a more widely used notion. So that makes sense.
Yeah, I think I think it does. I guess particularly in your case, it depends on what you chose as the sensitive attribute. So like depending on how you select that, it already determines what you mean by fairness in a way.
Yes, yes,
Right.
absolutely. Mhm.
Right. Sounds good. So I think the next question is from Mandarin. So if you're around, maybe you can unmute Mandarin. Okay, so she's not muting, so maybe I can repeat her questions. So she said like measuring the correlation between node representation and sensitive attributes can detect biases due to either node features or graph topology. Is that right? And can you also isolate whether bias comes from the node feature distribution or connections in the graph?
I see. Excellent question. And that's exactly what we are trying to do through the theoretical analysis. And as you mentioned, that the correlation kind of is a result of both the structural information and the sensitive attributes. Henceforth, through this analysis, we are trying to kind of isolate each part of them by putting them in each and every terms. For example, here, this little delta is the mean of the feature vectors. Sorry, the delta is the difference of between mu0 and mu1, where mu0 and mu1 are the means of features of different sensitive groups. And the delta is this large delta that I didn't introduce. It's actually the standard deviation of the distribution of different groups. So this henceforth delta isolates the bias come from the features. And you can see that the gamma 1 and the gamma 2, this gamma 1 only have terms that is relevant to, you see, theta size of different nodes. So it's somehow reveals the bias that lies in the fact that node population or node with different properties have different populations. And the gamma 2, you can see that it only has terms that is relevant to the degree of the nodes, either inter or intra-degree. Henceforth, it is trying to reveal the bias come from the connectivity patterns. So indeed, that you can see that the bias come from different sources, including features, nodes, and edges, which are the structures of the graphs. And through this analysis and as you suggested, to separate these different sources of bias, that allows us to develop algorithms that specifically cope with bias coming from features, node populations, and edge population. Yeah. I hope that clarifies.
I think so, but well, like okay, yeah. So she replied. So well, before opening up the floor for questions for other audiences, so I also got a question like, what would you like to share the slides with the audiences later on? So because I got a question from one of the audiences.
Sure. I'm gonna be happy to.
Yeah, so please send me the slides later on.
Sure.
So well, let's move on to like an open floor discussion. So anyone who has questions for the speakers, please feel free to unmute.
Yeah, hi, Yaning. Thanks for the nice talk. I had a question related to these sensitive attributes. So
Sure.
do you need to know them on all the nodes, or would it be possible if you just know like a random subset of the nodes? Can you still use your techniques?
That's a great question. So, first of all, in the training stage, for the augmentation design and the graph normalization scheme that we talked about, the sensitive attributes needs to be known for the training data. But of course, for the testing validation, nothing is assumed to be known. So that is this framework, but there have been works that can also cope with cases that only a subset or a part of sensitive attributes is known. Usually what we see is that those steps can be used before this scheme as well, because one idea you probably thought about is if only partial part of the sensitive attributes is known, then we could first try to interpolate or predict the sensitive attributes and then do learning framework, right? Yeah. So for these two schemes, we assume that the sensitive attributes is known. But I believe that additional steps could be taken so that you make these two schemes unknown as well. For the generative model, however, we don't assume the availability of the sensitive attributes because sensitive attributes are also generated.
Okay. Clear, yeah, thanks.
Sure, thank you.
So any other questions from the audience? So there's one just now coming up from Aliwasa. So maybe let me repeat this. So when talking about generative models, are we using the embeddings obtained from a generative model, or are we simply using the generative model to generate more graph structures to train a downstream GNN model?
And thank you for the question. So for the generative model that we are currently using, what the output of the generative model is a stochastic graph view. So it's the probability whether an edge exists or not. Henceforth, it is to directly answer your question, it is generating more graph structures to train downstreaming models for learning tasks.
Yeah, and the motivation is to avoid using the actual training graph for
Yes,
privacy reasons, right?
yes, absolutely. So the motivation is, as Tom mentioned, to provide people with a set of synthetic graph that hopefully, if we train on this synthetic graph, will achieve as similar utility as the real graph. Yeah, thank you very much for the comment.
So maybe I also got a question. So I mean, I am not sure whether I'm formulating the question well. So let me see. So as we are discussing before, so like somehow the sense or the fairness measure definitely depends on what are the sensitive attributes that you chose to be sensitive. So have you observed it in your experiments somehow, like does it really matters on whether one sensitive measure, so let's say that you do like some A/B comparisons, you try to choose feature A as the sensitive attribute, attribute A as the sensitive one, compared it to another choice of choosing attribute B as the sensitive one. So how does that kind of affect the structure that the network structure that you generate, for example, in the end? So I'm not sure whether I'm formulating this well, but
I see.
yeah.
I see. So you're specifically talking about the generative model, whether the choice of sensitive attributes will influence the structure of the generated graph.
Yeah.
Definitely, the answer is yes. So I didn't include another set of experiment, which we actually showed the structure of the generative graph. But on the high level, as I mentioned, that our analysis, let me just move quickly to that slide. So you can see that our analysis basically is built upon, not this one, this slide, built upon this analysis. Our design is based on this analysis, and which has two terms, alpha 1 and alpha 2. And in this alpha 1 and alpha 2, ignore all the other things. They are only relevant, mostly relevant to pk chi and pk omega, which is expected number of inter and inter edges. So somehow the idea of a fair generation is to achieve certain type of balance between these inter and inter edges based on the analysis. Henceforth, you're right. If we choose a different sensitive attributes, then this pk chi and the pk omega will be measuring different things, because what is inter edges and what is inter edges will be completely different based on the selection of the sensitive attributes. So henceforth, which attribute is considered to be sensitive is really critical, and it will influence what is your generated graph. It will only be balanced with respect to this type of sensitive attributes that you are selecting.
Yeah, so maybe it's still a naive question here. So in the generative model here that you in the graph generation task that you're trying to solve here, so when I generate the graph, do we need to specify the feature or those attributes on the nodes to generate them? Or like how can I embed this kind of sensitive attribute information into the graph generation?
I see. So I believe the way that it is done, okay, I am not the one who did the experiments or go into details. So
Yeah.
I believe the way is done is we first, even though we do not really know we do not really have hands on the ground truth graph, but what we did is you can see that it first we did adding noise and denoising part, right? So for the generated graph, basically what it does is it will have similar type of distribution. Henceforth, it's all stochastic view. So the distribution of the sensitive attributes and the distribution of the structure will be the same, but there's not a one-to-one mapping to the original graph in the sense that which node corresponds to which, because everything is giving you a stochastic view of the graph, and everything is with the probability of whether it is sensitive attributes 1 or 0, whether it is the edge are connected or not. Does it? I hope.
Yeah, yeah. I think I sort of understand the big picture here. Then, yeah. Thanks.
Yeah, thank you for the question.
So, is there any other questions for the speaker? Okay, so if not, then let's thank the speaker once again. And especially thanks for waking up super early to give this talk. I know it was 7 a.m. in California.
Yeah, and that is my pleasure. Motivates me to start my day early.